what's going on. All right. Question?
On the master set, either 3, 5, or 8, it doesn't have to be,
Which master set?
15 through 18.
I thought we didn't have to do that.
Oh, yeah, we didn't have to do it, but isn't it on the test?
It's a fair game, but it's not a major part of the test. But yeah, you said three, which ones?
Either 3, 5, or 8, whichever one you think, just one of them.
Well, I don't have the questions in front of me, I have the solution, so
Do you want
5, I can figure out what the question is, so.
Well, I can give you mine if you want. It's up to you.
Well, how about if I do 5, since I have 5 right here.
Thank you.
So basically, it's Newton's law of cooling problem. So we start at some temperature, so I'm just gonna use different numbers. So let's say we start at 150 degrees Celsius, and then it drops down to 120 degrees Celsius in some time. Let's say 15 minutes. So the question, in order to do a Newton's law of cooling problem, again, we're assuming that the environment is not changing its temperature much at all, that the heat is being lost, or gained, but heat is being lost to some really huge area where the heat gets dissipated and we don't notice it. Because if I put a really hot cube in the middle of the room, I'm probably not gonna feel that unless I get really close to it. So Newton's law of cooling is basically saying it's gonna lose the same fraction of what it could lose. So I need to know starting temperature, ending temperature, and how much time it took to get there, and I need to know the temperature of the environment. So if the temperature of the environment is, we'll just say 40 degrees Celsius. The question is, how much could we possibly lose? Well, I know that if I put some hot object in a room that's 40 degrees Celsius, it's not gonna get colder than 40 degrees Celsius. So the most it could possibly lose is 110 degrees Celsius. Well, it ended up losing 30 of that 110 that it could lose. So what Newton's law of cooling is telling us is that it's gonna lose 30 110ths every 15 minutes. That's the fraction it will lose every 15 minutes. So now we're at this point, so how much will it lose in the next 15 minutes? Well, what's the most it can lose?
30 and 1/10? 30 and 1/10? Or just 30?
So I'm looking, after 15 minutes it's 120 degrees Celsius, how much could it possibly lose?
40? 80?
80. It can get down to 40.
40.
But it can lose whatever that difference is, that's 80-degree difference. So how much does it actually lose? Because I know it's gonna lose 3/11ths every 15 minutes. So now it's gonna lose some amount over the amount that it could lose. And so that becomes math there, 24/11ths. 240 11ths. So that's 22,
21.8.
41.8. Okay, so that's how much it loses. Well, it's at 120 degrees Celsius and it's gonna lose 21.8 degrees Celsius. So after another 15 minutes, it will lose the difference there, 98 point. So that's the temperature after another 15 minutes.
It just keeps going in the same increment.
Yeah. So now, if we did another 15-minute increment, well, the most it could lose is that difference there, which is 58.2 degrees Celsius. That's the most it can lose. And it's gonna lose 3/11ths of what the most it can lose. So 3/11ths is equal to whatever the new change in temperature is over 58.2. trust you, it's gonna be smaller than that. So 15.9. So it was at 98.2, it's gonna lose 15.9, so whatever that number is.
Okay.
So the amount that it loses in each increment is gonna be less and less because, well, as it gets closer and closer to the room temperature, it'll get closer and closer, and officially it will never quite hit, but in reality, it gets so close that we can't tell the difference.
Can we go over E from this master set, the linear density? On page E.
All right, so on that one, by then you know what the speed is. So we basically have two formulas for speed for a wave that's traveling along some really skinny thing. We have the generic equation for a wave, which is frequency times the wavelength. And then in the case of something moving along a line, it's the square root of the tension divided by the linear density. Those are our two equations. And I believe in that problem, we know, by the time we get to part E, we know this, this, and this. So it's a matter of, so we just make up numbers. So if it's a 70 hertz string vibrator with a wavelength of, that's frequency, the wavelength 1.2 meters, and the tension of 1.7 newtons. These numbers are somewhat realistic. We'd end up with 70 times 1.2 is equal to the square root of 1.7 over mu. So that's the math problem. If you get it set up that, it's a calculator exercise. So I'm trying to find this. So the first thing I need to do is get rid of that square root. So I square both sides. So that's 84, I believe. So 84 squared is equal to 1.7 over mu. So that gets rid of the radical. Now I need to get this, I need to get mu by itself and on the top. Mu on the bottom is a lot harder to do. So there are a couple ways of doing it, but create my two fractions equal to each other, and then I can just do cross multiplication. I multiply the diagonal I know, and divide by what's left over. So mu would be 1.7 over whatever 84 squared is. And you get some number, and the units will end up being kilograms per meter.
Will we have all these formulas on the test that we're doing yesterday?
All of these formulas?
Well,
Yeah, I mean, I've got the linear density formula, I've got that on there.
Okay.
Yeah, I've got that one on there.
Frequency, period.
Yeah, I have frequency equals 1 over period, or F equals 1 over T. Period is 1 over frequency, or T equals 1 over F.
So we can leave that 1.7 over 84 squared, or we have to go?
At least, if you want to, the rule is 1 fraction bar per problem, and I consider the decimal to be a fraction bar. So whatever 84 squared is.
Okay.
So work that out, and if you want to leave it as a fraction, if you don't want to use your calculator at this point, well, you're doing 84 squared anyway. What is 84 squared?
7,506. Or 7056, sorry.
7.
Yeah, sorry.
All right. So if you're left with this, I probably would take off the point, because again, decimal and a fraction bar, but if you multiply top and bottom by 10, it's 70560. That would be an acceptable answer. But in the age of calculators, yeah, I'm expecting more than just leaving it like that. Well, I guess, I skipped some steps because you wanted me to start with I was dealing with part E, so assuming the rest of it you were fine with. Okay, did you need more detail on any of this? Okay. Any other questions? Kimberly?
I'm confused on the units, like, I don't really get what units to put for each. Like on the, for the waves and then for
For
the
the-
thermodynamics too, I get kind of confused.
It's a broad category there. So if, I guess there's the fact that temperature is in degrees Celsius or Kelvin, I mean, there are certain things that can't really be derived. You just need to know that if I give you a problem in degrees Celsius, you'll probably be dealing with degrees Celsius.
Okay.
The fact that hertz is a unit of frequency, it's helpful to know. But if you're looking at the formula page, where I say that frequency is 1 over the period, I have it written out in words and in symbolic form. So the units on the left side have to equal the units on the right side, which we can write more formally. The units of frequency is the units of the number 1 over the units of t. You have to know something at some point. You have to know the period would be a time. So the units would be 1 over seconds. And that's perfectly acceptable for a unit of frequency.
Okay.
It also just happens that that's equal to a hertz. So over here, linear density, I know density, regular density, is mass over volume. Linear density is mass over length. So unit of mass, kilograms, unit of length, meters. So kilograms per meter. That's how I do, this would be kilograms per meter here.
Okay.
Wavelength, it's a length, so meters. Tension is a force, newtons. I'm not quite sure really how to address the,
I think those are good.
okay.
Specific heat is calorie per million degrees Celsius?
Yes.
Okay.
Now, and on something like that, I mean, I have right there some specific heats, a specific heat of iron, a specific heat of water,
Okay.
and it's calories per gram degree Celsius there.
Okay.
Other questions? Okay, let's get this done. I will say that would make it very easy for me to grade. If you need extra paper, there's extra paper up here. When you're done with the test and you've handed it in, please staple it when you hand it in the correct order, please, in the correct order. And the this is what we're doing today, so when you're done with this, stick around if you're still working on stuff, or go if you're still, whatever.
If the terminal allowed, like, on paper, is there any way we can get that back and complete it? Like, all the assignments that we printed on paper?
For the assignments that are turned in on paper, I'm around all week, grades are due Wednesday at noon. So at that point, I've either graded it or not. So if you're around, you can stop by, or, you know, we have also the second 8 weeks, so if you need to pick some stuff up. But, as a general rule, if it's from this semester, which would be obviously our case, it should be in my office. If you've had me for some previous semester and you need it, the stuff's probably at home. So, so if you wait till January, give me some advance notice. And if you have to get 2 tests because the fine motor skills are on par with my normal, I'm not asking you to do it twice. Yes, the one up there. Sorry, one.
Thank you.
Thank you.